Hello everyone and welcome to the Data Idols Summer School. Welcome back to our community who have supported us for the last 5 years. I'm Adam and I'm a technical recruiter at Data Idols. To give you a little bit of an overview, the Summer School is a new pilot programme in partnership with the Data Science Festival. It will run live for 3 months so you can learn in real time from the comfort of your own home. These sessions are designed at introductory levels, so ideal for people who are starting their career in data and transitioning into data, students, all that kind of stuff. So please feel free to use the Slack channel. Watching this session, you're able to chat with other attendees. So use the channel Data Idols SS for any event-related questions, comments, or feedback. Thank you to all of our partners who have got involved with the Summer School. They've really helped to make this event a success, along with the mind-boggling 400 hours that it's taken our team to create this Summer School and make it a reality. All the sessions are pre-recorded, so you'll be able to look back at any time, at a later date, starting in September. We'll be emailing you with the link to watch the sessions back, and they'll be free to watch. So if there's anything you want to watch and learn at your own pace, you're more than welcome to do so. Today's session is with Harry from Hymans, and his session will be on an introduction to statistics. Thank you again for supporting the Data Science Festival in partnership with Data Idols, and enjoy the session.
Hello, everyone. So as you can see from the title of the slide, we're going to talk about statistics today, and this is going to be a short and hopefully sweet introduction to statistics. My plan for this talk is to actually help with some basic concepts around statistics. I will try to do that without even showing you a single equation. I'd like to focus more on the high-level understanding of these ideas and concepts. Hopefully, by the end of the talk, you'll be more interested in this, and you can take advantage of some of the links that I have on the last slide. This would be my advice, especially for anyone that wants to dig a bit deeper into statistics. But first, I'd like to give a bit of information about my background and connection to statistics. So what I've been up to for the last 20 years. That's a bit sad. Okay, 20 years, bloody hell. Okay, so I started with my undergraduate degree in mathematics. Then I continued doing an MSc in statistics and operational research in Athens. I am from Athens. Then I came to Glasgow to start a PhD in statistics, which after I completed that and did a couple of postdocs, one in Dublin, one back in Glasgow, I became a lecturer of statistics at the School of Mathematics and Statistics at University of Glasgow. For the last year, though, I've been working as a data scientist in financial services and specifically in Hymans Robertson. So again, before we start discussing about statistics, what I really want to point out at this stage is that I'd be really happy, extremely happy, if after the talk you start seeing the importance of statistics in different areas and start taking some of these concepts that we're going to introduce later on into account on what you are working on, whether that is research related or business related question. It's really important, though, to remember that sometimes these concepts take a couple of times for you to work on them and see them again and again in order to fully understand what they represent. Why do I say this? I say this because you shouldn't feel any pressure at all about understanding these things immediately. Sometimes these things take a bit of time. So let's discuss a bit about statistics now. Statistics and data are connected to each other. So let's start with having a short introduction on each one. And start with answering the big question, what is statistics? Well, there isn't a unique definition, but the one that I'm really fond of is the one you see on the slide. It's the science of collecting, analyzing, presenting, and interpreting data. And you see these four boxes on the slide. The really important thing that I'd like you to pick up, maybe you have already picked this up, is that the arrows, the connections that are between boxes, go both ways. This is really important because this process is iterative. And what I mean by that is, let's assume, for an example, that you've reached the presenting stage. You're presenting what you've done to an audience, and then you get a question that you didn't expect. And it's actually really normal to say, oh, actually, I need to analyze the data a bit more to be able to answer the question. So then you go back to analyzing the data. And then it could be that at that point you get what you want, or you're actually thinking, oh, wait a minute, in order to answer this question, I actually need to go back where I collected the data and get a bit more. And now I'll go back to analyzing and presenting. So as you could hopefully see, even from this, stupid small example that I just gave, this process is non-linear. You don't just go one way, you could go back and forth multiple times. What I also feel it's really important is that this process is independent of specific tools. It doesn't mean that you need to know R to be comfortable around statistics. No, you can use whatever language you feel comfortable. The things that I will show you, especially today, are independent of, oh, this needs to be coded in a specific way and things like that. So now that we've hopefully given an answer to what is statistics, let's be a bit more specific on each one of these processes of the statistical workflow. And let's start with the collecting part. The important thing here is that it's not enough to gather the relevant data. You actually need to understand how it was generated. And this usually it's highly interdisciplinary work. You could be working with a data engineer that gives you some information about where the data is, or maybe they collect it for you. You could actually be at the same time in a conversation with a domain expert. This is maybe financial data or data related to medical data that you have no connection about. So this is highly interdisciplinary work, and this is really important for you to also feel that it's not that a statistician needs to know everything about all these specific parts, and especially the collecting part. It could also be that the data may be available in a format that is not usable immediately. So you may need to do a bit of restructuring of the data at the start. What is also important especially for the last 4 or 5 years, is GDPR. GDPR comes to play since special procedures need to be followed. And finally, for this part, I really like the concept of garbage in, garbage out. You always need to remember this. If you have nonsensical data at the start as an input, your output will definitely be nonsensical, no matter how great you are in understanding statistics and techniques, and really have a knowledge of how you program the most efficient way. It's all about having the data that you want to answer the question that you have in mind. So if we go at the analyzing part, and just for the sake of it right now, on my mind, I've split it into 2 parts, even though it's way more than this. You could think of the first part there as cleaning and tidying the data, and possibly exploring relationships between different variables, performing some exploratory analysis at this stage. And at the second part comes the part of modeling the data. And this is a really important part because the optimal choice of the model depends both on the goal of the analysis and also the characteristics of the data, as we're going to see later on. So as an example, if your goal is to predict whether a customer will be interested in a new product, you will probably need a different model or different analysis than if you were interested at estimating a relationship between a task and how long that task took to be completed. Those are totally different things with each other. So different goals require different models. A question that you may have in your mind is, okay, wait a minute, what about speed? Well, how long does it take us to actually train the model to get the output? That's another thing that you have to keep in mind at this stage. A really important thing that you also need to remember is, who are you creating this model for? What are the needs of the model users? It could be that a black box approach is not good enough. Maybe in this stage, you need an easily interpretable model where you can explain its decisions to the user. As an example, it would be really good if some of you have created a model or are interested in creating a model, making the decision if a person should get a credit card or not, they should be declined. It would be really good if that model is interpretable. So if a person gets declined, they actually know the reason why they were declined, and they can actually go back and try to fix this before they apply again, instead of just getting a simple, no, you were declined, that's it. And you actually can't even help them to tell them why they were declined. So finally, on presenting and interpreting the results, you can actually see this maybe as communicating and visualizing the results. There, the key to analyzing data using statistics is to be able to communicate the approach and results effectively, and my personal feeling is also simply, with your colleagues, stakeholders, and the general public. And if you see what I did there, I put different levels of expertise on the possible audience. Colleagues, so people that may know exactly the same as you. Stakeholders, people that are domain experts in different things. And also general public, maybe people that haven't seen these ideas ever before, and this is the first time that they hear about them. It's not easy to communicate results into different audience, and this comes again with experience, but it's always really good when you start getting some data to always ask, okay, what is this for? Where do I need to present it? Because this will help you for all the previous parts also. So I might have used the word data 100 times already. So let's have a closer look at data. And we'll start with different types of data. And in this case, I've put a simplified diagram of all the possible types that we may encounter when dealing with data. So on the left-hand side, we have numerical data, where the observations are numbers. And this could split into two different parts. Let's say we have discrete scale, where there are a number of possible values. Or the continuous scale, well, there are uncountably many different possible values, so it's not even possible to list them all. We're going to see something like that really soon. On the right-hand side, we have the categorical scale, where the observations in this case are categories. And again, there are two parts or sections here. We have the ordinal scale, where the categories are actually naturally ordered, or the nominal scale, where the categories are simply names or labels. Again, I'm trying to think about what you might be thinking right now. And one of the possible questions could be, why do we care about different types of data? Well, we care about it because different statistical procedures exist for different types of data. And these different statistical procedures, they also have different assumptions that we need to actually see if they hold or not. So we need to know what kind of data we have to know what kind of procedures we can use. But besides the need to use the correct statistical procedure for the data that we have, we also need to make sure that all the computations that we're making and visualizations are sensible. So as an example right now, it wouldn't make sense to try to find the average hair color of a specific group. It doesn't make sense. What does this mean, average hair color? So right now I have a wee bit of an exercise for you here. And I've put 4 different variables there. And my question to you is, which data type is the best match for the following? So we have temperature, number of kids, hair color, and educational experience. Here's a great time for you to pause the video, because in about 5 seconds, I'm going to start giving the answers. So in this case, we have that temperature is a continuous variable because it could be, we could have a temperature 23 degrees or 24 degrees in Celsius, but we could also have every possible number in between. And there are infinite numbers in between 23 and 24. So for the number of kids, well, actually that's discrete. You could have 0, 1, 2, 3 number of kids and so on. Now for the hair color, this is definitely a categorical variable, but we're also saying there that it's a nominal variable. It doesn't have a natural order, and this kind of makes sense. You could have a person with brown hair and another one with red hair. It doesn't make sense that there is an order between brown and red. On the other hand, though, for educational experience, besides being a categorical variable, this is what we call an ordinal variable. Because if you think about it, there is a specific order. In order maybe to go to university, you need to finish high school. In order to probably go for a PhD, you need to have finished your university degree before that. So we talked a bit about data. Hopefully you feel a bit more confident about recognizing what data type it is that you have in your work and what you're working on. Let's spend a bit of time right now on a bit of the statistical jargon that we need to know and try to bring a bit of life into it by using some actual examples. Let's start with population and samples. What does each one represent and what are their differences? So let's consider the following. Does a new drug reduce the number of deaths in patients with heart disease? What effect will changes in climate have on the average surface water quality? And finally, what is the average age of people that have completed a marathon under 3 hours? Now, each of the 3 previous questions refers to a target population. In the first question, the target population is all patients with heart disease. And each one of them, each patient, represents a specific case. Now, the majority of the times, we are not able to collect data for every case in a population. Imagine right now trying to get to have all these patients that have a heart disease and put them somewhere and try to give them this drug and see if it works. That's not easy. Collecting those data for an entire population is called a census. A census is difficult, as I just gave an example. It could be really expensive to actually do a census. A lot of times, though, it could actually be impossible to identify the entire population of interest. Imagine on the third example, to try to get all the marathon runners that have a personal best below 3 hours. It's not easy to find these people. Marathons are happening every day, and a lot of them, the results are not even available online. You can't find them accessible anywhere that you can immediately use. So what do we do instead? You actually take a sample. A sample is the data you have. And ideally, a sample is a large fraction of the population. You've taken a large proportion of the population, but that's not also necessary a lot of times. But as an example here, we could focus on the third question that I have there and try to find 20,000 runners with a personal best below 3 hours and take this sample data to actually get an average age from the sample and use that as an estimate for the population. So just to summarize, a population is the large group of individuals under consideration, while a sample is a subset of the population selected as being representative of that population, and each of whom will have the variable of interest measured. Finally, and before we take a short statistical break, let's discuss another 2 really important concepts around statistics. These are parameters and statistics. Most statistical procedures are about understanding, interpreting a numerical summary. We could have something like through our statistical study of 1,000 runners that have completed the marathon in less than 3 hours, we have computed that the average age is 38.3 years old. So a numerical summary can be calculated on either the sample of the observation or the entire population. So in this case, we have calculated a numerical summary on the sample. We had 1,000 runners, and we found that on that sample, the average age, is 38.3 years old. That is actually a statistic because it's a numerical summary based on the sample. If you have a numerical summary based on the whole population, that is called a parameter. So again, to actually try to bring this all together, a population parameter is a single number summarizing in some way the values of the variable of interest in the population, while a sample statistic does that, but for the specific sample that you have. And as you can think of, this provides an initial estimate of the parameter. Now you might say, okay, why do I care about statistics and parameters? The reason why we care a lot in statistics about these things is that a major aim of what we're doing is to actually make conclusions about the value of the parameter based on the value of the statistic that you have. So there's something that you don't have, the value of the parameter. There's something that you do have, the value of the statistic, of your sample statistic, and you're trying to say, okay, so this value of the statistic, could it be actually different than the value of the parameter? Imagine at this example that you initially started your question with saying, I believe that the average age of those runners of the whole population is 40 years old. So that was the initial value that you put for the parameter. Your sample said 38.3. And then you're using statistics to see, is this actually different, or did I just see the difference because I used this sample? That if I take a different sample, it's going to be 41 or something different. So let's now have a short exercise that helps us pick up all the concepts that we've talked about so far. We've asked more than 2,000 professionals the following question. After an average work day, how many hours do you spend on pursuing activities that you enjoy? And we found that the average time from this sample to be 2.13 hours. Now, your job right now is to determine which of the following is a sample statistic, an observation, a variable, or a population parameter. And I have the 4 options for you below. You have to connect each one with the correct option before. Again, a good time for you to pause the video right now and think about this exercise. And I'll be a bit bad right now and tell you that I'm not going to show you the answer on the next slide. You can communicate with me and get back and forth and discuss this, but I'd really like you to even work amongst each other and try to figure this out by yourselves. So right now, for the statistical break that I promised earlier, I want to give you a story, and this is a real story. You can find even more information about it online. And it's about, I'm taking us back a bit. So during World War II, the RAF, the Royal Air Force, lost a lot of planes to German anti-aircraft fire. And as a result, they decided to armor their planes up. And the whole question is where to put the armor. And it's not an easy question to answer. A lot of you may think, oh, let's put it everywhere. I don't know. Well, we're not sure where it should be, so let's put it everywhere. Well, you don't want to be making so much armor for every plane. That's a lot of resources. And also, the more armor you put on the plane, the heavier, and as a result, slower the plane becomes. So this is a bit of a tricky issue. You need to think of this a bit better. So what did they do? They looked at planes that had returned from the missions, counted up all the bullet holes in various places, and they turned to a statistician, Abraham Wald, and they turned to him in order to find how to minimize bomber losses to enemy fire. So this image shows some hypothetical data. This is not the real data, but imagine we had something like this in front of us. You had a picture of a plane, and you had where all the bullets of all the different planes were. So you see that you have a lot on the wings, you have a lot also on the back of the plane, and right here at the center. Now, if I'd ask you right now, after you've seen this picture, where would you put the armor for the plane? What would you tell me? What would you think of putting the armor, and why? And again, another good time to maybe pause the video, because I'm going to give you the answer really soon. So what Abraham Wald thought about when he had all the numbers at his hand was thinking that the damaged portions of these planes, of these returning planes, they actually show locations where a plane can sustain the damage and still return home. Those planes that hit in the other places presumably did not survive, and that's why we didn't see them at all. This is known in statistics as survivorship bias, and this can lead to overly optimistic beliefs because the failures are being ignored. Imagine as a different example that you're trying to analyze financial performance of companies the last year, the companies that existed during last year, and you also at the same time exclude all the companies that went bankrupt sometime last year. That's a bit unfair. These companies should also be included in order to show the financial performance for last year. So just to sum up here, the armor shouldn't go where the bullet holes are. It should go where the bullet holes aren't. And as I said before, the reason planes were coming back with fewer hits to the engine was that planes that got hit in the engine weren't coming back. And just to bring a connection to everything that we were saying earlier, is in this case, the sample that we had, the hits on the planes that safely returned, did not represent the population, the hits on all the planes. So we were using a sample to infer something on the population, but the sample was focusing on something different, not on the population that we had in mind. So this again shows you that besides the whole statistical jargon thing that you need to keep in mind, there's a lot of thinking that needs to happen and making sure that you're always measuring the correct thing or thinking about the correct thing. So now let's go a bit about summarizing data. We've shown the different types of data. Now let's see how we can summarize these types. And again, I try to make it a bit simplistic here because I've assumed that for a lot of you, this is the first time that you may hear these things. I've split it into numerical data and categorical data. So for numerical data, the distribution of the sample, of where the sample values are, is summarized in terms of location, spread, and shape. Location refers usually to the center of the distribution. What's the average value? What's the median value? The spread refers to the range of the values that the data take. Some data may take values from here to here, while other data may take values from here to here. So there is a smaller variability on the second data set that I just made up out of my mind. Finally, we also care about the shape of the distribution. When you look at the data, is it symmetric around the center? Is it skewed towards a specific side? Are there maybe two different modes? So all these things, we need to actually have ways of visualizing them, which I'm going to show you later on. And for categorical data, what we usually care about there is proportions and percentages to summarize the data. So let's introduce right now what is known as summary statistics to summarize the data. So I've mentioned these things before, but again, I'm assuming that maybe this is your first time. So mean and median. The mean, which is often called the average, is a common way to measure the center of a distribution of data. The median is found by arranging all the values that we have in ascending order from smallest to largest, and identifying a value that divides this whole population or sample that we have into two groups with, as near as possible, the same number of observations in each group. And here what's important for you to remember is that we could compute a mean or a median for the entire population in the same way that we could do it for the sample. It's just that we're looking at a different data set. The mean, though, and especially the sample mean, is greatly influenced by outliers, by large observations, or by observations that have totally different values than all the other observations. Imagine if you had 11 observations, the first 10 of them was all the integers from 1 to 10, 1 to 7, 8, 9, 10, and then the 11th variable with the 11th value was the number 200. And you try to find the average value of those 11 values. As you would understand, the average value would be greatly influenced by that 200. The same thing, though, wouldn't happen when you're looking at the median. And this is why a lot of times we say that the median is a robust measure of location. It doesn't get affected by outliers that much, as especially the mean. Another measure of location that it would be good for you to have in mind is the mode. The mode can be thought of as the most common value that we have in the data. The mode also, as a result of its definition, the most common value, is also robust to outliers. Now, statistics is all about variability. The variability in the data is extremely important. We could have a research question that is something like, is the difference that we see in the two groups of patients because of the different drugs that we gave to each group, or is it totally accidental? Did that just happen? You know, I just had these samples, it happened. If I take two different samples, I'll get something totally different. The two most common measures of variability are the variance and the standard deviation. Again, I decided to keep everything non-formulaic in the literal way. I didn't put any formulas here. Both of them, I would say variance and standard deviation, they're a bit tedious to calculate by hand. You can do that, but obviously at any software that you use, it does it for you. I would say right now, and again on a high level understanding, that the standard deviation is the easier of the two to comprehend, as it roughly describes how far away the typical observation is from the mean, the distance of the typical observation from the average value. And again, if you want to think of an example of this, which I should probably already had one of these in my slides, but I just thought about it. You could think of the following. Let's assume right now that you have two basketball players and you're checking for both of them what is their points during the last 10 games. Player A, for the last 10 games, and for each game actually of the last 10, they've been scoring 20 points each game. Player B, on the other hand, for the last 10 games, sometimes he or she has a good game, and they score 30 points, a really good game. But other times, they're not that good, and they score 10 points. And this happens the whole time. So for the last 10 games, you have 30, 10, 30, 10, 30, 10. Now, if you go and find the average value for player A, you're going to get that it's 20 points per game. If you go at player B, you're still going to get that it's 20 points per game. The difference there will be on the variability of those values. If you look at player A, that they've been consistently scoring 20 points, the standard deviation, how far away a typical observation is from the average value, is 0, because the average value is 20, and the typical observation, well, each observation that we have is 20. So the distance is always 0. When you go though and compute the standard deviation for player B, you're going to see there that it's not zero. There is a bit of variability there. There is a bit of distance from a typical observation from the mean. Hopefully that example was again, really sorry, I should have included something in this slide to explain this. So now let's sum up, and I've named this slide so far so good with a question mark. I'm hoping that there is no question mark and you're feeling good about it. But if you don't, as a reminder, refresher, we've answered the question, what is statistics? We showed the different types of data. We differentiated between population and sample and parameter and statistics. And at the end, we discussed summary statistics. The really important thing that may come to your mind right now is, okay, is this all I need? Can I do everything by using summary statistics? The answer is no. Let's have a visual example of why the answer is no. So this is a famous data set that it's called Datasaurus. And you might have guessed it why it's called Datasaurus is because one of the 13 data sets that comprise this data set, it's showing a dinosaur. And that's not the really interesting thing. The interesting thing is that all these 13 different graphs have been created. Obviously, each one has an x-axis and a y-axis, so you're looking at two variables. But each one of those graphs has the same summary statistics as any other graph. So if you go at the dinosaur here and you try to find the average value for x, you're going to get that it's 54 point something. The same thing for the mean of the y, the same thing for the standard deviation, and the same thing for something that I didn't mention earlier, correlation, which can be thought of as a measure of the linear relationship between these two variables. What is really important is that if you just had the summary statistics here, you couldn't immediately say, oh, I know what's happening. I'm just going to present the summary statistics. That's not true. Because if you look at the first graph, you would say, oh, there is no connection between x and y. Things are a bit random. On the second graph here, you could actually say, oh, you know what? As the x-axis is increasing, we have higher and higher values. The values for y are lower. So maybe there is a negative relationship between these two. But on the third graph, we see the opposite. And if you see at every graph, you have a totally different structure. So what is the takeaway from this? The takeaway is never trust summary statistics alone. Always visualize your data. So in order to get the whole picture and finding out what is really happening with the data, you need to actually draw a picture. And that is not always easy, and it's a bit of an art, but I can promise you that this is something that you become better and better with time, with experience. So let's actually right now see why visualization is important and finish up the whole section of showing some different ways of visualizing data. Now, before visualizing data, before showing the ways of visualizing data, some of the ways, I wanted to give you a couple of more reasons of why we might be interested in this. And you've already seen one. You've already seen that the data actually, by visualizing them, may show a pattern that I didn't expect or I didn't see at all from looking at numbers, summary statistics. It may actually already help us answer the question that we have in mind. Equally as important, later on, when we actually need to do a bit of modeling, we may take a lot of the things that came from the graph and put them in some way for our modeling later on. So it could be that we see that a couple of variables have a specific, let's say, quadratic relationship. They go like this. Well, then maybe we should take that information from the graph and inform the model that, hey, be careful. When you have these two variables, try to have a quadratic relationship between them. So these are all really important things. Let's have a look right now. I want to break down some of the important visualizations that you mainly see in statistics. So a bar plot is a really common way of displaying a categorical variable. And here I'm using a famous data set about cars, can be found online, where on the x-axis we have the number of cylinders that cars may have, and on the y-axis you have the number of the cars that had these cylinders. And you can also think of this bar plot that can be converted into proportions. So instead of looking on the y-axis at counts, we could have percentages there. Now, taking it one step further of going into two categorical variables, I've done the easy thing because you will have to do the difficult thing. I've actually only put them in a table. Your job is to see how this could be created in a bar plot. And I also wanted to inform you that this table of trying to summarize data for two categorical variables is called a contingency table. So in this case, we can see that in this sample that we have 16 female cats and 32 male dogs. So it gives us a high-level overview of what we have from each specific combination. What I would really like you to think of is maybe think of how would you actually visualize, even in a piece of paper, you don't have to do this in a code, in a piece of paper, how would you visualize the previous contingency table in a bar plot? And I also want to put in this slide a couple of really important graphs that you need to keep in mind in general and Google later on. Mosaic plots, pie charts, and waffle charts. I'm not a really big fan of pie charts, but to be fair, they are used a lot, so I didn't want not to include them. So going at the numerical data summary, we could start from a dot plot, and sometimes in this case, we're interested in the distribution of a single variable. And I think a really good start then is the dot plot. So in this case, we have on the x-axis the miles per gallon, and on the y-axis, we have all the different cars that we have available. So we get a bit of an overview of, oh, you know what? There are a couple of cars where the miles per gallon are more than 30, some that are less. You get a bit of a high-level overview of what's happening there. Now, what happens if you want to take this a bit further down the line and actually view data for two numerical variables? Well, then you can use a scatter plot. And scatter plots are extremely helpful in quickly spotting associations relating variables, and whether those associations come in the form of simple trends or whether those relationships are a bit more complex. Again, it would be really good right now if you try and see if this graph that I have right here for you, if it makes sense. I'll explain what is on the X and Y axis. On the X axis, we have the weight of cars. And on the y-axis, we have the miles per gallon. And it looks like there's a bit of a negative relationship. Does that make sense? And why? Another graph that we use a lot in statistics is called histogram. And I've always think of the histogram as a natural extension of grouping the dot plot. So a dot plot shows the exact value for each observation. These are extremely useful for small data sets, but imagine if on the previous dot plot, instead of having 30 cars, we had 30,000. That wouldn't look nice. You wouldn't be able to see what's happening. So rather than showing the value of each observation, we prefer to think of the value as belonging to a bin, a range between two values. Those bin counts are plotted as bars into what is called the histogram. And before I show you the end result, I put there a really nice link by Aaron Lunzer and Amelia McNamara that show how a histogram is being created from raw data in a really nice interactive way. Now, this is how a histogram looks at the end of the day. And this is me taking the dot plot from before and making it the histogram. So you could see here that for the miles of gallon, we see that the mode, the most common values that we see are around here, are a bit after 15 miles per gallon. We could also go and see if that's the case. 15 is right here. So we could go vertically at 15 and we see, yeah, there are a lot of values here. So that makes sense. So that provides, I think, a bit more information on what's happening here. The really important thing, there are a lot of important things about histograms. Feel free to connect with me in some way and we can get into this a bit deeper. The really important thing that I want to leave you with the histograms is be wary of the length of the bins that you choose. If you change the length of the bins and instead of going from 15 to 15 and a half, going from 15 to 16, so going up 1 instead of a half, the counts inside change. And as a result, the bars, the length of each bar changes. So you may see something different. What I always do when I create a histogram, I always play with different values for the width of the bin and see if there are any significant changes. If they're not, I feel comfortable about it. So finally, I cannot not mention the box plot. A box plot summarizes a data set using 5 statistics while also identifying unusual observations. I'm not going to go really into deep with what the box plot has, what are the 5 statistics of this box plot, but I want to give you at least 3 of them right now. So right at the center in this horizontal line, you see the median value. That's specifically here, we can say that the median value for all the cars that have 4 cylinders is close to 20, let's say 26, 25 and a half. This vertical line here, so the end, let's say, of the box, this is the 3rd quartile. And the 3rd quartile is the value that 75% of the observations are below it and 25% of the observations are above it. If you see right now at the bottom of the box, where the box essentially starts, this is the 1st quartile. And this is a bit of the opposite. 25% of the observations are below it, while 75% of the observations are above it. Now, these lines that you see at the start and at the end, they're actually created as functions of these quartiles. But what you need to have in mind right now is that these lines show us the length that we're willing to go before we call something an outlier. So if you see right here of the number of cylinders at value 8, when we have a number of cylinders 8, you see that right here at the bottom and at the top, we have 2 outliers. By the way, if you hear a child crying, that is Jason. He just came back from nursery. Hopefully he's going to get better really soon. Or even more, hopefully you're not able to hear him at all, and these headphones are really doing the work. So these also, another big thing that you need to remember right now about box plots, and a thing that I don't like when people say this, they say, oh, a box plot shows the distribution of the data. That's not true. A box plot shows 5 statistics of the data. Actually, I would tell you to try and see alternatives to box plots that show the distribution of the data. One of it is called a bin plot. Please have a look at this online because that gives you a bit of information about the distribution, while the box plot doesn't. So just to sum up, and we're coming to the end of the talk, what does a statistician actually do? So a statistician, as we said, is someone who uses mathematical techniques to analyze and interpret data and draw conclusions. And as I said before, they typically do the following: decide what data is needed to answer questions, determine methods for finding or collecting data, doing the same thing and trying to answer the questions that they have, and also report conclusions from their analysis. I wanted to also mention something that I consider extremely important. We take these things for granted, but unfortunately, sometimes we don't work on these things as much as we should. It's extremely important to ask an interesting question. It's probably the hardest thing to do in this process. Here's where you need to spend some time understanding what you actually want and think about possible limitations of the data that you have, and will they be able to answer what you want. You also, I feel, need to perform various sanity checks. I feel that when I see something that I expect, I'm always saying, oh, that's a bit strange. I expected this to happen. I need to double check it. I need to perform different sanity checks to make sure that this makes sense, this is okay. You also feel you need to create documentation to minimize potential errors. And I'm not referring only to documentation about your code, but documentation about what you're actually doing, what is the technique doing, and why you're doing this. And finally, you also need to think about two really big things in statistics, data science, machine learning, the whole science in general, reproducibility and replicability. I don't want to go into depth for those two things, but there are two amazing papers that I've put the links on. Please have a look at them. Minimal statistical knowledge for you to understand each one of those. They're a bit general, which I really like about them. So just to sum up, there are, as you might know, there are various free and really high level resources available online. Some of them, I wanted to put them right here for you. So I put 3 books there, and I've tried to split the books into a stat book that is really nice, really good. And I've actually taken a lot of the examples and ideas for this talk. Another really amazing book about data visualization, and another book specifically about a language, but again, using it for data science and statistics. And also for those of you that you learn a bit more by videos, and hopefully you've learned a bit from this video also. There are, again, really a plethora of really nice tutors and channels available online. For me, 2 of the top ones, obviously you might know of Khan Academy, but I also want to give my kudos to Brandon Foltz. Really nice resources about statistics available for free from YouTube. That's about it from me. I hope you've enjoyed the talk. If you have any questions or you want to connect with me in any way, you'll have available my LinkedIn and Twitter account. Feel free to do that. Take care.